Good morning, students. Myself, Vaidehi, working as Assistant Professor in Sri Muthukumaran Institute of Technology. Today, the video lecture is from the subject CEC 334 Analog IC Design for 6th Semester ECE students. Today, the topic is from the Unit 2 of High Frequency and Noise Characteristics of Amplifiers. The noise plays a crucial role in determining the performance of high frequency analog and RF systems. We will discuss the major noise sources, noise figure, noise modeling techniques, and practical methods used to reduce noise in amplifier circuits. First, we see about the introduction to noise in amplifiers. Noise is an unwanted electrical signal that interferes with the desired signal. In amplifiers circuits, noise limits sensitivity and reduces signal quality. There are three major types of noise. The first one is thermal noise, which is generated due to random movement of charge carriers in resistive elements. The second is flicker noise, also called 1 over F noise, which becomes dominant at low frequencies. The third one is short noise, caused by the discrete movement of charge carriers across semiconductor junctions. To evaluate amplifier performance, engineers use noise figure abbreviated as NF. A low noise figure indicates better amplifier sensitivity and performance. Next, we see the noise in single stage amplifiers. Single stage amplifiers are the basic building blocks of analog circuits. The three common configurations are common source, common gate, and common drain amplifiers. Each topology exhibits different gain, bandwidth, and noise characteristics. The major noise sources in these amplifiers include MOSFET channel thermal noise, gate-induced noise current, and thermal noise from feedback resistors. A commonly used technique in low noise amplifier design is employing an inductive load in a common source stage. This improves both gain and noise matching simultaneously. Next, we see about the noise figure and noise factor fundamentals. Noise figure is one of the most important parameters in amplifier design. Noise factor is defined as the ratio of input signal to noise ratio to output signal to noise ratio. A noise factor greater than 1 indicates that the amplifier adds noise to the signal. Noise figure is simply the noise factor expressed in decibels. A low noise figure means less degradation of signal quality. Another important concept is the optimum source admittance, represented as Y optimum. By presenting this optimum impedance to the amplifier input, designers can achieve the minimum possible noise figure. Next, we see about the flicker noise versus white noise. This slide compares two important noise types. Flicker noise or 1 over F noise dominates at low frequencies. Its power increases as frequency decreases. White noise, on the other hand, remains nearly constant across frequency and dominates at higher frequencies. The transition point between these two regions is called the corner frequency. For low frequency applications such as biomedical instruments and sensor systems, reducing flicker noise is particularly important. Next, we see about the noise in differential amplifiers. Differential amplifiers offer significant advantages over single-ended amplifiers. One major advantage is common mode noise rejection. Noise that appears equally on both inputs is largely cancelled. Noise sources in differential amplifiers include transistor channel noise, tail current source noise, and mismatch between devices. At high frequencies, different amplifiers generally provide better linearity and improved noise performance. For this reason, differential architectures are widely used in RF communication systems, mixed signal integrator circuits, and precision analog applications. Next we see about the noise modeling in low noise amplifiers. CMOS low noise amplifiers or LNAs are essential components in modern wireless communication systems such as 5G, Wi-Fi and IoT devices. Accurate noise modeling is necessary because modern short channel MOSFETs exhibit complex noise behavior. The dominant noise source is usually channel thermal noise. Additional contributions come from gate-induced noise current and substrate noise coupling. Advanced noise models help engineers predict amplifier performance and optimize transistor sizing, bias conditions, and matching networks. Next, we see about the practical noise reduction techniques. Several techniques are used to reduce noise in practical amplifier designs. The first is impedance matching, where the source impedance is adjusted to achieve minimum noise figure. The second is multi-stage amplifier design, which contributes gain and minimizes overall noise contribution. Resistive feedback improves stability and bandwidth but must be carefully designed because resistors themselves generate thermal noise. Inductive source degeneration is a popular technique in RF circuits because it simultaneously improves noise figure, gain, linearity, and impedance matching. Next, we see about the real world amplifier performance. This slide presents examples of commercial amplifier products. The Keysight two-stage low noise amplifier achieves approximately 22 dB gain with a noise figure of about 1.4 dB at 5.5 GHz. Texas Instruments high-speed amplifiers provide extremely low voltage noise and very high bandwidth. Analog Devices offers wide band amplifiers operating from megahertz to gigahertz frequencies with stable gain and low noise characteristics. These examples demonstrate the practical trade-offs among gain, bandwidth, power consumption, linearity and noise figure. Finally, we came to the summary and the key takeaways. Let us summarize today's discussion. Noise is a fundamental limitation in amplifier performance and directly affects signal sensitivity. Single-stage amplifiers exhibit different noise characteristics depending on the topology and operating conditions. Differential amplifier provide superior common mode rejection and improved noise immunity. Modern CMOS low noise amplifiers rely on accurate noise modeling, impedance matching, and inductive degeneration techniques to achieve excellent performance. As semiconductor technologies continue to evolve, improved device structures and advanced noise models will enable even low noise figures and higher frequency operation. Thank you for your attention, students. Hope you all understood. Thank you.